Hello everyone, my name is Ahmed Hazimi. I'm a researcher at EPFL in Switzerland in the field of system security with a focus on fuzz testing. I will be presenting our paper, Magma, a ground truth fuzzing benchmark. This is joint work with Adrian Herrera from the Australian National University in collaboration with the Defense Science and Technology Group and with Matthias Bayer from EPFL. Fuzzing is a dynamic software testing process through which a program is evaluated for the presence of bugs by feeding it procedurally generated inputs. Indicators of faulty behavior are typically crashes and resource exhaustion. However, fuzzers go beyond random generation of inputs. Over the past decade, tens of fuzzers have been published, some targeting specific applications, others claiming performance improvements across the board. Fuzzing performance is typically quantified as one of the code coverage the fuzzer achieves, the number of crashes the fuzzer finds, or the number of ground truth bugs the fuzzer triggers. These metrics present a challenge in evaluating fuzzers and especially for making any sound comparisons. For starters, code coverage is subjective. Each fuzzer may define its own form of coverage and format to encode it. With differences in semantic and syntactic representation, comparing raw coverage information across fuzzers is not feasible. Alternatively, comparing fuzzer performance based on a unified coverage metric, for example edge coverage, may result in lossy measurements. A data flow optimized fuzzer may measure and maximize data flow coverage, and evaluating it based on control flow coverage metric will misreport its performance. Similarly, crashes are inaccurate. Previous work has shown that the number of crashes is often inflated by 2 to 3 orders of magnitude in comparison to the number of underlying bugs. Crashes are often deduplicated by fuzzers based on their coverage profiles or stack hashes. Using different coverage metrics or different stack hashing techniques results in different unique crash counts for the same set of crashing test cases. Crashes are thus not suitable for measuring or comparing a fuzzer's ability to find bugs. To evaluate a fuzzer's bug finding capabilities, having an indicator of what bug was triggered and when is crucial. More importantly, those bugs must be real to more accurately represent realistic fuzzing workloads. Moreover, the targets in which those bugs occur must also be real, to reflect the complexity of software in the wild. In practice, existing ground truth benchmarks do not satisfy those requirements, as they provide either synthetic targets or synthetic bugs. With Magma, we focus on providing an accurate measure of realistic bugs discovered through ground truth knowledge of the root cause. Fuzzers are typically evaluated on a set of targets sourced from one of the following benchmarks. Bugbench and Google Fuzzer Test Suite both contain real programs with real bugs. However, each target only contains 1 or 2 bugs on average. This sparsity of bugs, combined with the lack of automatic methods for triaging crashes, hinders the adoption and makes both benchmarks unsuitable for fuzzing evaluation. Google Fuzzbench, the successor of Fuzzer Test Suite, relies solely on coverage profiles as a performance metric. The CGC sample set provides a wide variety of ground truth bugs and targets, but the relatively small size and simplicity of its synthetic workloads does not enable thorough evaluation of a fuzzer's ability to explore more complex programs. The LavaM benchmark provides real targets sourced from core utils, but it injects synthetic bugs of a single type, out-of-bounds memory access triggered by a magic value in the input. This bug does not represent the statefulness and complexity of bugs encountered in real-world software. Unifuzz is yet another ground truth benchmark with real targets and real bugs. However, it lacks ground truth knowledge and it is unspecified how many bugs each target contains. This puts it on par with most commonly used targets for evaluating fuzzers, namely open source software. Although real-world software is used, the lack of ground truth knowledge about the triggered crashes makes it difficult to provide an accurate, verifiable, and quantitative evaluation. Several factors must thus be taken into account when designing a benchmark. Relevance, which requires that the benchmark assess a system within its intended application domain. Verifiability, where measured performance maps back to a verifiable set of features of the system being evaluated. Usability, where a benchmark should provide ease of use and present no barriers to entry. Fairness, where a benchmark is not biased towards some feature of the systems under evaluation. And finally, reproducibility, where a benchmark should reproduce consistent results given the same set of initial conditions. However, the stochastic nature of fuzzing presents challenges for developing a benchmark with these properties. For example, reproducibility requires that the same results can be produced consistently for a particular test environment, but individual fuzzing trials vary widely in performance. A fuzzer may also actively modify the test environment, for example, by transforming the target or generating new seed inputs. This differs from traditional performance benchmarks like spec CPU, where the workloads and their inputs remain fixed across all systems under test. This leads us to define the following set of properties that we argue must exist in a fuzzing benchmark. Diversity, which states that the benchmark contains a wide variety of realistic bugs and targets. Verifiability, where the benchmark yields verifiable metrics that accurately describe performance. And usability, where the benchmark is accessible and has no significant barriers for adoption. With these properties in mind, we developed Magma, a ground truth fuzzing benchmark based on real programs with real bugs. Magma is diverse. It is a collection of 7 targets with widespread use in real-world environments: libpng, libtiff, libxml2, Poplar, OpenSSL, PHP, and SQLite3, and Lua and libsoundfile have been added in later versions. Magma is verifiable. Its workloads contain over 100 bugs for which ground truth is easily accessible and verifiable. These bugs are sourced from older versions of the 7 targets and forward ported to the latest version contained within Magma. Through the use of canaries, information about bugs reached and triggered is readily available. And Magma is usable. It imposes minimal requirements on the user, allowing fuzzer developers to seamlessly integrate the benchmark into their development cycle. It provides a portable framework to integrate new fuzzers and targets, run evaluations, and report results and comparisons. And the forward porting process proceeds as follows. For each target, we manually inspect bug and vulnerability reports to find bugs that are suitable for inclusion in Magma. For example, ensuring the bug affects the core database and not some external utility. For each bug, we first inspect the bug fix submitted by the developers and revert it to reintroduce the bug to the latest version. Next, we insert minimal source code instrumentation, what we call a canary, to collect data about when a fuzzer reaches or triggers the bug. This process of forward porting is applied through diff-style patches to the target's codebase. Upon completion, the codebase is modified to apply this transformation and obtain a Magma target. Forward porting is a manual process which spans an entire range of complex tasks, from searching for relevant bug reports to inferring Boolean trigger conditions and inserting the canaries in the code to flag bugs at runtime. The complexity of this process renders any automatic approach error-prone or virtually infeasible in practice, ultimately yielding fewer bugs of lower quality. Dedicating human resources to the forward porting process maximizes the correctness of Magma's bugs. Magma's targets were selected for their diversity and functionality. They incorporate program behavior that typically poses a challenge to state-of-the-art fuzzing techniques, including magic values, recursion, compression, checksums, and global state. To quantify this diversity, we apply principal component analysis over the benchmark's workloads. This highlights the distinct set of functionalities each Magma target exercises. We use Intel pin to capture execution traces of the different targets. Then, we classify the instructions into Intel Z categories, which capture a higher level semantic description of an instruction than its opcodes. This evaluation highlights the spread of Magma targets across the principal components, which confirms their diversity and functionality. Magma also contains 118 bugs, spanning 11 CWEs, summarized in this figure. Magma has the second largest variety of bugs by CWE, following the CGC sample set, and the second largest bug density following LavaM. However, as discussed previously, both CGC and LavaM lack the properties necessary for use as a fuzzing benchmark. Namely, both consist of synthetic targets or bugs. Moreover, CGC results are not directly verifiable, and LavaM's artificial bugs have unrealistic densities and distributions. Magma's bugs are real, and they reflect challenges encountered by fuzzers in real-world scenarios. Magma uses 3 bug-centric performance metrics to evaluate fuzzers. Reached, which refers to a bug whose faulty code was executed, but the condition to trigger the fault was not satisfied. Triggered, which refers to a bug that was reached and whose triggering condition was satisfied, indicating that the fault has occurred. And detected, which refers to a bug that was triggered and whose resulting fault was observed and flagged by the fuzzer. The symptoms of a fault are not always directly observable, so this metric evaluates a fuzzer's ability to detect different types of faults. Magma also provides a runtime monitor that collects real-time statistics from the instrumented target. This provides a mechanism for visualizing the fuzzer's progress and its evolution over time. We evaluated Magma on a set of 7 mutational fuzzers, the majority of which claimed incremental improvements over AFL. To validate those improvements, we completed 24-hour and 1-week evaluations using the entire Magma target set as benchmark. We repeated each campaign 10 times to account for the stochastic nature and behavior of fuzzers. In general, the more bugs a fuzzer can trigger across different targets, the better its performance and the more portable its capabilities are. Magma's ground truth instrumentation allows us to accurately measure bug triggering events. In this figure, we demonstrate the average number of bugs triggered by each fuzzer across each of the 7 targets. The plot is also supplemented by a statistical significance measure based on the Mann-Whitney U-test to validate the observed difference in performance. Areas with a darker green color indicate a stronger significance, meaning a fuzzer was significantly better or worse than another for a specific target. The significant test shows that AFL, AFL Fast, AFL++, and SimCC AFL performed similarly against most targets, despite some minor differences in mean bug counts. However, the figures also show that AFL++ scored the highest mean bug count against LibTIF, and that this difference is statistically significant. Meanwhile, FairFuzz displayed significant performance regression against libxml2, OpenSSL, and PHP. Magma thus allows us to accurately measure real bug counts as opposed to approximate crash counts, thanks to its ground truth instrumentation. In addition to bug counts, we use the time required to trigger an event, reached or triggered, as a measure of fuzzer performance. Fuzzer campaigns are typically limited to a finite duration, so it is important that time to bug discovery is low. In these figures, we plot the Kaplan-Meier estimator to model bug survival time, which is a measure of how long a bug survived the fuzzing process before being triggered, with the upper limit being the entire length of the fuzzing campaign. Sharp descents indicate consistent behavior. For example, in figure C, SimCC AFL always triggers bug AAH020 around the 12-hour timestamp. Meanwhile, a plot that does not intersect the x-axis before the 24-hour mark implies that the bug survived at least one of the campaigns, such as bug AAH018 with FairFuzz in figure A. Out of the 43 bugs triggered by the fuzzers under evaluation, 19 bugs took on average more than 20 hours to be triggered. This suggests that fuzzers still have a long way to go in improving their program exploration capabilities. However, while many of the Magma bugs are difficult to discover, there is a set of 17 simple bugs that all fuzzers find consistently within 24 hours. These bugs provide a baseline for detecting performance regression. If a new fuzzer fails to discover these bugs, then its program exploration strategy should be revisited. Finally, we would like to note that these reports are reproducible as part of the open source Magma framework. Magma is actively maintained and constantly updated both by us and by the community. It has received over 40 pull requests for new features and fixes, and for introducing new targets. Magma has contributed to other fuzzing-related research, such as evaluating crash deduplication methods and measuring the effects of different coverage metrics on fuzzer performance. We made Magma available as an open source project at the following URL. Feel free to use it and contribute to its development. If you'd like to add your fuzzer to be part of Magma Suite, or to add a target suitable for evaluating fuzzer capabilities, make sure to create a pull request on our GitHub repo. Thank you.